Hey everybody! This is going to be a quick physics review on vectors and forces and how to put the two together. So let's go through two examples on how to apply forces and vectors. Here's our first example. Here I have a sign. I want to hang this sign. It's a 10 kilogram sign. It says physics is fun. So I'm hanging the sign, but I don't want to hang it just from a string up and down. I want to hang it with this situation here. So imagine this is a wall. I have a rope pulling this way on it, and I have a bar kind of holding it so it doesn't wobble around. You see this all the time. So the first thing I need to do is draw a free body diagram on that sign. So one of the forces acting on that sign is the force of gravity, pulling straight down. Now, if the sign is 10 kilograms, the force of gravity is m times a. M is 10, and a for gravity is 9.81 meters per second per second. So 10 times 9.81 is 98.1. So there's 98.1 newtons of force pulling down on this sign. Sweet. Awesome. Now, we also have a force of this rod or whatever. So the rod is pushing on this wall, and the wall is pushing back on the rod. So the rod's kind of pushing to the right, holding it up so it doesn't drop like that. And the rope has a force pushing or pulling this direction. So there's tension in that rope. The tension in the rope is pulling this way. We'll call it Ft. Ft for tension. Okay, so now what I'm going to do is I want to analyze what is the amount of force in that rope needed to hang this sign. So what I need to do, since this rope is at a weird angle, at 30 degrees, it's not a weird angle, but since it's at an angle, not vertical or horizontal, what I'm going to do is I'm going to break it down into a vertical force and a horizontal force. So I can imagine that that rope is pulling up on this sign with 98.1 newtons of force. It has to be 98.1 newtons of force because it has to cancel out gravity. If it was less than that, this thing would fall. If it was more than that, this thing would lift up, and neither one of those is ideal. So 98.1 newtons of force has to be lifting up. And then the other component of that tension is going to be pulling to the left with some amount of force. And then, so this leftward force is going to cancel out the rightward force of this rod this way. So these two forces cancel out, and these two forces cancel out, gravity and the vertical component of tension. So what I can do is anytime you have a force that's at a weird angle, not vertical or horizontal, you can always move the arrows around as long as you keep them in the same direction and the same length that you originally drew them. You can always move the arrows around and physically place them wherever you want. And I want to physically place them so that they make a triangle. So I'm going to take this arrow right here and I'm going to pop it over there. So I make a triangle with those forces. So my triangle looks like this. This side of the triangle, the hypotenuse, is the force of tension. This side of the triangle is whatever I can call this arrow here. And then the vertical part, is this 98.1 newtons. Awesome. Now, since I have a 30-degree angle here, I have to know an angle and a side, and I can figure out the rest of the triangle. Or I can also do it two sides as well. So I need two pieces of information, and I can figure out the rest of the triangle. So my goal is to figure out what is the tension in the rope. Well, now I'm going to use my triangle math here. So I drew a triangle, I labeled all the parts. Hypotenuse, opposite, adjacent. I have 4 equations written down the board here. So what I'm going to do is I'm going to figure out what do I know. According to this triangle, good news for us is this triangle matches up perfectly with this triangle. So you can just literally plot in the things. Sometimes you have to rotate the triangle around to get it to match up this one. So I know the angle. I know the angle is theta. So I'm given the angle. So angle. I know the Ft, that's my h. Well, I don't know it, but I'm trying to figure it out. And then I know over here is the opposite side. I know the O. So, to figure out the equation I need to use, I need to find an equation with angle, h, and O in it. And the reason I said so dramatically is that you can remember it was so ka toa. And so is sine, S-O-H, so. So, we have sine of the angle equals opposite of our hypotenuse. So I put in sine of 30 equals opposite would be 98.1 over hypotenuse, which is ft. Now I have my equation. Now I just have to rearrange it and solve. Now sine of 30 in your calculator, if you type in sine of 30, hit equals, you will get a number. It's just a number. It equals 0.5. You have to make sure your calculator is in degree mode and not radians. It'll get 0.5. So this changes to 0.5 when you type it in. So 0.5 equals 98.1 divided by ft. I'm going to multiply both sides by ft. So this side cancels out. And then I'm going to divide both sides by 0.5. And so 98.1 divided by 0.5 is equal to 196.2 newtons. So here's an example where the force of the rope has to be stronger than 98.1 newtons versus an example we went before in class where the force actually went down. And the reason is because there's only one rope instead of two. So there's our first example. Let's go through a second example on ramps. Let's ramp things up! Alright, so now let's imagine I have this object on a ramp. The first thing I want to do is figure out the forces on this object on this ramp. So, I'll go with a different color here. One of the forces acting on the ramp is gravity. Now, just like before, if I have gravity, it's pointing straight down. So, I'm going to draw, I got a little ramp thing here. I'm going to draw a force of gravity just like this. It's my dot, boom! Gravity's pulling straight down, and it has a force of 98.1 newtons. It's just the same as what a force we had before. 98.1 newtons of force are pulling straight down. Then I have my reaction force, and the reaction force always points 90 degrees to the surface. So I'm going to use my thing here, is pointing 90 degrees to the surface. Alright, so it's going to be like this. Boom, there's my reaction force pointing that way, Fr. And then I would have friction as well. Now let's say that this thing is in equilibrium. That means that the frictional force, that means it's not moving. That means all the forces have to cancel out. Friction is going to go up the ramp. So I'll draw my little protractor here, or straight edge, or the friction. So those are the three forces acting on the object, and it's not moving. But it's not clear that it's not moving because it's hard to see this example. So what I'm going to do is I'm going to redraw this example so it's a little bit neater, so we can think about vertical forces and horizontal forces. So instead of drawing my ramp like this, I'm just going to look at it from a different angle. I'm going to tilt my head a little bit, and I'm going to draw it like this. So here's my ramp. Boom, boom, boom. This is my angle theta. This is my log. And now, drawing those same forces here, I have gravity going this way, Fg. I have reaction force going this way, 90 degrees, going 90 degrees to the surface, which is straight up now, Fr. And I have friction going up the ramp, which is Ff. So now, what I can do is I can look at those forces and say, you know what, one of these forces is not nice looking, meaning it's not vertical or horizontal. I want all my forces vertical and horizontal. So, what I can do is I can take that gravity, because that's the one that's not vertical or horizontal, and I can split that gravity up. Part of that gravity force is going to pull it down into the ramp, based on this picture, it's going to pull it down with an equal and opposite force as that reaction force right there. So I'll call it Fr, because it's equal to the reaction force. They have to be equal forces. The other force has to oppose friction because this thing's not moving in this example, so it has to point this way. So the other part of gravity is going to point this way. We'll call it maybe Fa for the applied force of gravity. So gravity has this applied force that's pushing it down the ramp. And these two forces are basically the components of gravity. Now, once again, I can take that gravity force, I can move these arrows anywhere I want as long as I don't change the direction or size of them. So I'm going to move this arrow down here, call it Fa, and here we have a triangle, just like before. And the cool thing is, this triangle is the same as this triangle. I'm going to show you. It's the same thing. It's the same. I just had to rotate it around. So this angle right here is theta. So whatever the angle of the ramp is, now if you turn your head again, you can see that ramp again. Whatever the angle of the bottom of the ramp is the angle of this top part of the triangle. So what does that mean? Well, how does that help us? Well, that tells us we can actually have two equations we can derive with this. The equation for reaction force can be solved because I have a triangle here. Now, this is the angle. I have to rotate my triangle around to make it look like this, but this is adjacent to that angle. Adjacent, and I have hypotenuse. The hypotenuse is gravity. So the reaction force is equal to, well, solving for it, it's going to be cosine. So I'm going to use cosine of angle equals adjacent over hypotenuse. Do my little substitution here. The hypotenuse is gravity, that's the force of gravity. And the adjacent side is my reaction force. So multiply both sides by gravity, force of gravity, times reaction, cosine of angle is reaction force. Now there's a way to find force of gravity, there's another way to write this. It's mass times 9.1, or mg. So the equation for reaction force is force of gravity times cosine of the angle, or mg times cosine of the angle. And a similar argument, this side is the opposite side, and we have the hypotenuse. So we're going to use sine, because sine of the angle equals opposite over hypotenuse. Opposite is going to be FA. Hypotenuse is going to be FG. So multiply both sides by FG. And then replace FG with M times G. We get that the applied force, or the force sliding down the ramp, is equal to mg sine of the angle. Okay, so we have those. Now, how do we use them? Well, going back to our ramp here, maybe we want to figure out what does the coefficient of friction have to be? Maybe that's the question. What would the coefficient of friction have to be if this angle is 30 degrees? Angle is 30 degrees. What would the value of the coefficient of friction have to be to make this work so it doesn't move? Okay, well, I don't need this anymore because I have my equations. And these are equations that I'll write down in your notes. Reaction force is equal to this. Applied force of gravity is equal to that. And also in your notes, remember that frictional force equals coefficient of friction times reaction force. So we're going to use these three equations as same thing with the net force equation to solve. So really, if you want to, let's start with the net force equation. All right, F net equals, now what I'm going to do is I'm going to write it like I did before. F net would equal MA, would equal, going back to the picture I erased, applied force is going this way, friction is going this way. Applied force is going down the ramp, friction is going against the ramp, so it'll be FA minus force of friction. So, to wrap things up, we're going to actually come up with an equation putting everything together on objects that can slide down ramps. How do we solve those? So, substituting things in, here's what we have. F net equals MA equals your applied force, which we know an equation for the applied force. So be more specific here. Applied force is mg sine theta. Mg sine theta. Minus frictional force. Frictional force is coefficient of friction times reaction force. Coefficient of friction times reaction force. But I can even go even more specific here, because I know what the reaction force is always going to equal. So instead of writing reaction force, I'm going to write what reaction force is actually equal to, mg cosine. So I'm going to replace this with mg cosine of angle. And there you have it. This equation right here is for objects on ramps or inclines. You can use this equation to figure out, like, let's say you go sledding or skiing or something, and you start on top of the hill and you slide down the hill with friction. Or you could think about an object being pushed up a hill or something. Whatever the case is, anything on a hill or an incline, is going to have this acceleration in this equation. And here's what you can know. Let's look back at our example here. Do I know what m is? Yes. Do I know what a is? No. Well, actually, let's say it's not moving, then a is 0. If it's equilibrium, a is 0. Or I can use SUVET to find a, or if I can leave it blank for now. I know what m is. I know g is 9.81 meters per second per second. Do I know the angle? Yes. It's 30 degrees. Or I can solve for the angle. Depending on what I know, I can plug it in and solve. So I know the angle, sine angle. Yeah, I can plug that in. Do I know the coefficient of friction? No, but maybe I can solve for it. So back to this example, if I wanted to apply it to this particular example, well, my m I know, my a is 0, so I know that side. I know m, I know g, I know sine of 30, I know that. I don't know coefficient of friction. I know m, I know g, I know cosine of angle. I can plug that in. So I know everything in that equation except for coefficient of friction. Let's say I were given the coefficient of friction, 0.2, and I wanted to figure out what the acceleration is. Maybe it's not 0 anymore. Well, now, just a different variable that I know, so I plug in coefficient of friction and everything else and solve for A. Let's say I didn't know what the mass was. Ooh, that's a little trickier. Say I didn't know what the mass was. Well, the cool thing is, there's a mass in every single term. There's a mass in every single term. So really, if there's a mass in every single term, it cancels out. And if I want to figure out what the mass was, I can use one of these two equations to solve it. I could use one of those two equations to solve it, because if I knew FA and the angle and G, which I always know, I can figure out the mass. Or if I knew FR and the angle and G, I could solve for the mass. So with these combinations of equations, you can solve for lots of things. The frictional force, coefficient of friction, reaction force, any variable you can think of. Acceleration, coefficient of friction, all for stuff sliding down ramps. So this is the equation to use for objects on inclined planes, objects on ramps, things like that. And it comes from triangles and the net force equation. So hopefully that makes sense. Have a great day and happy vectoring, if that makes sense.